We did some bonding, and we got into geometry, I believe, and a reminder that there's two types of geometry that we talked about. There is the electron pair geometry, which describes the geometry of the electrons around the central atom. And that's usually where you do geometry from, always the central atoms, the most important. And there's also the molecular geometry, which is also sometimes referred to as the shape of it. Now, as we saw in certain cases, these names are the same. And they will be the same names when really we only have one type of electrons around the central atom, when we only have bonding electrons. So when we only have bonding electrons involved, no non-bonding electrons, no dots. Both the electron pair geometry name and the molecular geometry name will be the same, because essentially in that situation, as we talked about, as those electrons move, they're attached to the atom, and that atom they're bonded to will also move with them, and they'll end up in the same geometry and so forth. It's only when we start to sort of incorporate non-bonding electrons, we will end up with a different molecular geometry name when we do have non-bonding electrons or lone pairs on the central atom. And the reason for that is a couple. It is the different type of electron interaction that we talked about. There's sort of three types of electron interaction. There is bonding versus bonding, which is sort of acceptable. There's also bonding electrons and non-bonding electrons, so kind of lines and dots in your Lewis structure. That's getting a little worse. And really the worst type of interaction is non-bonding electrons near non-bonding electrons, so kind of like dots near dots in your Lewis structure. That's the worst situation. So when we do start to have non-bonding electrons, we're also missing the atom that's bonded to those non-bonding electrons in a bonding situation. And what that does allow is for the electrons really to kind of get away from each other a little bit more, kind of move a little bit more, because they do not have that extra atom in the way that kind of gets in the way of them getting too close to each other. And that's what ends up happening, is we do end up getting the same shape, but a new name for the shape, but a different name for the electron pair geometry. Electron pair geometry is always based on how many electrons there are. Remember as well, when we're doing geometry, we do want to count everything pretty much as one electron pair and one bond. Even if you have a single bond, double bond, or triple bond, it doesn't matter. Pretty much everything counts as one. They're effectively just working as one electron pair and one bond. Any questions on any of that? Yeah. Say again? A radical, it will work the same way. You still do it based on you would still do it based on basically the central atom. If the central atom does have one unpaired electron, you would probably still count it as sort of almost like a pair of electrons around there. Just there is something in terms of electron density in that area. Yeah. Other questions? All right, then we're going to continue on here. Chapter 4. The next thing we're going to talk about is actually what's referred to as hybridization. Now, the idea of hybridization is that we do see certain sort of bond angles associated with certain molecules, and sometimes not one bonding theory like Lewis bonding theory there, just drawing Lewis structures, maybe adequately explains what's going on. So this idea of hybridization came about, and Valence bond model describes a covalent bond as basically an overlap of orbitals, and we have that region of overlap here where we're going to be sharing those electrons in this particular case. Now, what happens though, if you kind of think about it, is if you're trying to perhaps overlap a p orbital with like an s orbital, in theory, they have different sort of shapes and designs. And they're also usually at different energy levels a little bit. So they're not exactly at the same energy level. They don't exactly have the same shapes or anything like that. So it can create perhaps not the angles that we would expect to occur. So hybridization tries to sort of explain that and come up with a new way of bonding. that does sort of account for some of the things that we do see in terms of angles and so forth. So atomic orbitals, and again, atomic orbitals are what we've been talking about, our S's, our P's, our D's, and so forth, our atomic orbitals. A proper energy and orientation in the same atom are hybridized. So hybridized orbitals are mixtures of atomic orbitals that come together. They result in basically orbitals that have the same shape. They also are all going to be kind of the same energy. So that's going to allow for better sort of overlap of those orbitals and better bonding to sort of occur. Now, when we do make these hybrid orbitals, the total number of hybrid orbitals that we make is equal to the number of atomic orbitals that we basically put together. So if we mix 3 atomic orbitals together, we will end up with 3 hybrid orbitals that are made in that particular case. So the simplest sort of hybrid orbital you could have results from a combination of an s orbital and a p orbital, and that is what is known as sp hybrid orbitals. So if you think about it, when we talk about s orbitals, there's basically one s orbital, there are 3 p orbitals, and of course for our d's, right, there are 5 d orbitals. So in the case of an sp hybrid orbital, we're going to take our s orbital, which is the spherical type shape there, and there is our figure 8 p orbital sort of happening right about there. Maybe red's not the best color there. And we're going to basically mix those together. So we're going to grab an s and we're going to grab a p orbital and basically mix them together to make this hybrid orbital. Now, these are our atomic orbitals over here. And I just grabbed a S and a P, that is 2 orbitals, which means when this goes through hybridization, you will make 2 equivalent, what are known as sp hybrid orbitals. You could kind of see over here, I don't know, kind of like a kidney type shape they kind of make. 2 sort of lobes that are kidney type shapes. They are going to be 180 degrees apart. Now, hybridization is linked to electron pair geometry that we talked about. And when we have 2 electron pairs, that is the linear geometry, right? 180 degrees. So that's like 1 and 2. So that's just like 2 electron pairs. We're going to do geometry there, and it will have 180 degrees linearness. Now, when we do this, by the way, we will see and talk about, we will have what are referred to as unhybridized p orbitals in this case. We actually will have 2 of them, the py and the pz orbital, and we'll have 2 unhybridized regular old run-of-the-mill p orbitals that are unhybridized as well. So sp hybridization goes with the linear electron pair geometry. That's basically like our 2 electron pairs. So for example, if we look at beryllium fluoride, beryllium here is an exception to the octet rule. It is number 4. It has an electron configuration of 1s2, 2s2. This is beryllium, basically, we're looking at here. Beryllium has 2 valence electrons, and that is these guys right here. So in the process of hybridization, what occurs is there's always 1 electron that goes from kind of the lower energy level. It gets pushed up to the higher energy level. So one of these electrons here is going to make its way up to this p orbital that's empty. And the result of that is we will now have basically 1 electron in the p orbital up there and 1 electron in the s orbital. And those are going to be the 2 high atomic orbitals that are going to come together to make our hybrid orbitals. Again, you can see at this point they are at different energy levels. Again, they're different shapes. Now we make our hybridization. We have some lower energy, a little bit more stable orbitals that are both the same shape. They both are the same energy level. And we also have, as I mentioned before, those 2 unhybridized p orbitals up on top. And it's going to be this sp guy that's going to then go and basically make a bond with a fluorine, and he's going to make, for example, a bond with the fluorine. Again, this is beryllium all the way across here. And again, they have obviously a way to make that bond is they have one unpaired electron, which will allow them to share an electron with fluorine and make the bond that they need to in this particular case. Any questions on that there? All right, so that is sp hybridization, much like the name sounds like, taking an S and a P, putting them together. The next type of hybridization is what's known as an sp2 hybridized orbital. And again, much like the name implies, in this particular case, we're going to take an S and two p orbitals and basically mix them together. So you can kind of see here, there's our S, which is our sphere. There's one p orbital there and another p orbital coming out at the other sort of angle there on the orientation. We're going to mix those together, and since we took one S and two P's, that will give us three equivalent sp2 hybrid orbitals that are going to be made. Again, they are both going to be, all three of them are going to be same energy level, same shape. They actually will end up in this triangle type of shape, and it is 120 degrees apart from each other. And I don't know, this is, how many letters did I use in this? 1, 2, and 3. So that's kind of like our electron pair geometry of 3 electron pairs, and that is our trigonal planar, right? Geometry, trigonal planar. And again, it's going to have 120 degrees difference. In this particular case, we actually have one unhybridized p orbital that's still there. So we still have one p orbital that's unhybridized in this case. So sp2 is basically trigonal planar. It'll end up 120 degrees. And again, it makes 3 equivalent sort of, as you can kind of see here, hybrid orbitals where it's kind of bigger and just a little kind of node at the end of there. And that's our hybrid orbital happening in this particular case. There's 3 of them right there. So if we take a look at an example of this, boron trifluoride, also an exception to the octet rule. We are looking at boron's electrons here. And again, boron there is number 5, which is 1s2, 2s2, 2p1. And these are the 3 valence electrons that boron has. In this case, as it goes through hybridization, the same thing is going to occur. This lower energy electron is going to get promoted with a little bit of energy up to the open p orbital, just like how we do it with orbital diagram. It will actually go into the one to the right there, not the same one. So again, maximizing parallel spin. And that's going to give us that promotion. And at this point, we are then going to grab the s orbital and those 2 p orbitals, and we're going to hybridize them to make 3 equivalent hybrid orbitals that each now have an electron in it. And as I mentioned before, our pz orbital, which is that last one, is unhybridized in this case. That's good because now each of these borons here, atoms or hybrid orbitals, has the electron to make a bond with each of the fluorines that are there, right? And can make its sort of sigma bonds, as we'll talk about in just a second, with each of those hybrid orbitals. Any questions on that there? Now, continuing on in terms of hybridization, so we have basically sp2, which is basically related to trigonal planar geometry, electron pair geometry. The next type is sp3 hybrid orbitals. And sp3 hybrid orbitals, much again like the name implies, is going to take everybody there, your S and your P's here. And we're basically just going to grab them all. And because we took 4 atomic orbitals, we will create 4 hybrid orbitals that are sp3. Again, each of them same shape, each of them same energy. And again, you can see in this case, that is the bad choice of color there because you can't see anything. Let's try that one. We got our p orbitals on each of the axes there, still our s orbital. And once again, they're going to come together in this bond angle that is 109.5. And that also should seem familiar to you. I just used 4 letters. That's kind of like 4 electron pairs. And that's going to be related to our tetrahedral geometry at 109.5 degrees in this case. So in this case, there is no unhybridized p orbital. They all are being used in this particular case. And an example of that would be methane, CH4. Again, if we look at carbon, 1s2, 2s2, 2p2 there, I think. And this right here are the 4 valence electrons that we see in carbon. Same thing's going to happen here. We're going to promote up one of those lower energy electrons up into the higher p orbital. And that's now going to give us basically an electron in each. And then everybody's going for a hybridization trip. And again, we're taking in here 4 individual atomic orbitals. And that's going to give us our 4 basic hybridized orbitals. Each of these from carbon has the ability to bond to our hydrogens that we have in CH4 as well. So everybody could go through hybridization, actually except hydrogen. So hydrogen does not go through hybridization. And that is because it only has basically 1 electron. So these would be bonds between an sp3 hybrid orbital in carbon and a 1s orbital there in hydrogen, which is the only orbital it actually has all the way across there. They're each sp3 to 1s orbital bonds that are happening in this case. Now, we usually apply hybridization usually to the central atom, but truthfully, you can apply hybridization to any outside atom if you like. But a lot of times we do it for our individual sort of guy in there. Now, this is sp3, but let's talk a little bit about sigma bonds. And sigma bonds are bonds where the orbitals do what is referred to as head-to-head overlap. They basically just go straight at each other, straight onto each other, and they overlap just coming straight at each other. And that is what's basically known as a sigma bond. If you want to think about it in a very plain sense, any single bond is like a sigma bond, basically. So any single bond, first bond that happens will be that type of overlap of those orbitals. They're just going to come straight at each other. And that overlapping region, again, is where we would be sharing those electrons to make the bonds. Now, if we take a look at something like NH3 here, oh, look at NH3. So if we take a look at NH3 and we take a look at really all the sort of bonds that are happening here with NH3. What we will see is if we take a look at the nitrogen, which is 7 there, 1s2, 2s2, 2p3, and that's going to be the 5 valence electrons that nitrogen has. So what happens in this particular case is we have in our 2s, again, it's only the valence electrons involved in bonding, so we don't show, obviously, the lower energy electrons. It's got a couple of electrons, and we come up here to our 2p. We have, obviously, an electron in each of these. So this is sort of it in a starting position for our nitrogen. And what's going to happen in this particular case is we will get this electron going upwards. Now, different in this case is our p orbitals up there already have electrons, right? So this electron will end up, just like we do orbital diagram, it's going to end up back over to this side. And what that's going to do for our nitrogen now is we will have an electron there in our 2s and our 2p. And we'll go this way. And this will then go through hybridization. So what type of hybridization is this going to go through? So here's really the quick way that you can do hybridization. It's very much like this. You just go like S and like P, and we'll do some D. So we want to count the electrons around the atom that we're going to do hybridization for the exact same way as we do it when we do geometry. Because it is related to the electron pair geometry, we still want to count single bonds, double bonds, and triple bonds as basically just one electron pair. So here, we're still counting basically everything as one. So when we look at the nitrogen, it's got 1, 2, 3, and 4 electron pairs. So here's a super quick way to figure out hybridization. You start at the bottom here and go 1, 2, 3, and 4. I use an S and 3 Ps, which means this is going to hybridize as an sp3 hybrid orbital. So basically that is how you know what that's going to hybridize. What that means is this s orbital here and all 3 of those p orbitals are going to come together to create now 4 identical in terms of energy hybrid orbitals, which are sp3 in this case. Bless you. And we basically have this situation occurring, right? Now, if we think about our bonds here in NH3 and even our lone pairs as well, I'm going to number them, just randomly numbering, no order in particular here. I'm going to call that 3, 1, 2, and 3. So we have an available sp3 on our nitrogen here to make a bond with the 1s orbital of hydrogen, right? Because it's got an electron. So that's going to be, say, bond number 1 there, right? We also have another available sp3 hybrid orbital here in nitrogen that can make a bond with a hydrogen 1s orbital as well. We'll call that bond number 2. And lastly here, we have one more bond. Let's just go upwards because I'm running out of room. This guy's available to make that third bond with the 1s orbital there in hydrogen to make our third bond. So if we think about all the bonds here, we just accounted for every bond with our hybridization, but there is still something left, right? There is still something left on this structure, and that is the non-bonding electrons here on nitrogen, and that is accounted for right here. So this hybrid orbital is going to be holding the non-bonding electrons, which is why it has no ability to make a bond at this point because it is full already, right? It has 2 electrons. No orbital could have more than 2 electrons. So it already has the 2 electrons, not available to make bonding, but it can be non-bonding electrons. So with the hybridization model, we could also account for the non-bonding electrons that we see there, in addition to the bonds that we make as well. In this case, we would have 3 sp3 1s bonds between the nitrogen and the hydrogens. And by the way, every single one of those bonds are a sigma bond, yeah? So they're all sigma bonds here. Head-to-head overlap, those are all sigma bonds, single bonds basically, meaning the orbitals are just going to come straight at each other, head on with each other, not from the side or anything like that. Any questions on that one there? Now, we could also apply this hybridization to something like water. And if we take a look at water here, and we do our oxygen, which is our center atom, 1s2, 2s2, 2p4 there. And those are the 6 valence electrons in oxygen. If we draw oxygen, but we draw oxygen with our water here, we will end up with this. So again, I want to apply hybridization to my oxygen in this particular case. So again, we're just going to roll with the simplest way to apply hybridization. How many electron pairs are around the central atom there? It is 1, 2, 3, and 4. So I'm just going to come over here and just start marking off at the bottom and go up. 1, 2, 3, and 4. That's an S and 3 P's, which means the hybridization of this oxygen is sp3. Yeah, so that's like the simplest way you could assign hybridization, pretty much just like that. Any questions on how I got there? Now we can see what's happening with water here. Let's redraw it one more time. And we'll call this bond 1, bond 2. We'll call this 3 and 4 in terms of lone pairs. And we're going to have, in terms of our orbitals here, we'll have a 2s, which has a couple electrons in there. Our 2p, which has 1, 2, 3, and 4. Again, through the hybridization process, we're going to bring this electron up. Once again, just like an orbital diagram, it's got to go down to the middle one, as the guy on the left is full, so it can't go there. And that's going to result in 1 electron there, couple there, and 1 there. Now it's going to hybridize as sp3, which means we're just going to take everybody here. And since we took basically 4 orbitals, we are going to create, once again, 4 equal sp3 hybrid orbitals. Now, if we just kind of keep track of what's going on here, we'll just kind of do it in order. This guy is filled. This guy is filled. This one has 1 electron, and this one has 1 electron. Again, what that's going to allow is for some bonding to occur here. For example, this sp3 hybrid orbital, again, all this is oxygen, right? This oxygen's hybrid orbital has the ability to bond with the 1s orbital from hydrogen, as again, hydrogen will not hybridize. So that's going to be like our first bond we see there in water. This guy also has the ability to hit that 1s orbital there from hydrogen and make our second bond. And now what we are left with are our lone pairs, and we can account for each of those lone pairs. Right here, number 3, we could call that number 3's lone pairs, right? And right there, number 4's lone pairs as well. So once again here, our hybridization accounts for both non-bonding electrons and also bonding electrons within a molecule. Any questions on that? Once again, each of these are going to be sigma bonds, the ones that are bonds. So these both would be sigma bonds basically here. So that sp3 hybrid orbital and the 1s orbital are just going to go straight at each other, and they're going to have an area where their electron density overlaps, and that is where the bond is going to basically occur from. Any questions on that there? Now, let's take a look at a couple other ones. Let's talk about C2H4 here. So if we were to draw a Lewis structure for C2H4, it will look something like this. It will actually have a double bond in this particular case. So we're going to look at carbon here and try to get our hybridization. And again, carbon is number 6 up there. 1s2, 2s2, 2p2. It's got its 4 valence electrons. So we want to do our hybridization here of our, we'll call this carbon number 1, and we'll call this carbon number 2 in this case. So again, we want to do our hybridization. So I'll just make my little sketch here of my orbitals. And we have actually, in this case, 2 central atoms. So I believe we talked about this at the end last time. If you have 2 central atoms, you basically will kind of hold your hand over one half of the molecule and look at the other half, and then flip it around and hold your hand on the other half. So in this particular case, what I'm going to do is blank the screen, but then unblank the screen. I'm essentially going to highlight it. This is like I'm holding my hand over that part of the molecule, right? So I'm not even going to be concerned with that part of the molecule here. I'm going to try to figure out the hybridization here of carbon number 1. So in this particular case, we still do, as we talked about last time, count that bond that's going into carbon number 2. So we still count it. So in terms of electron pairs, we obviously have one there, right? We have one there. And just like when we do geometry, our double bond, triple bond, single bond does not matter. Everybody's counting as one. So we essentially have 3 electron pairs here. So again, we start here at the bottom, 1, 2, 3. In this case, that's an S and 2 P's, which means the hybridization of this orbital is, or this carbon is an sp2 hybrid orbital. Any questions on that one there? I am now going to just kind of switch it around, and what I'm going to do is move my hand to the other side there and try to erase that without killing everything. Not bad. And now what I'm going to do is essentially put my hand on this side of the molecule so I can look at carbon number 2 and basically do the same thing. Once again, that bond in the middle does count for both carbons. So we're going to count up our carbon number 2's electron pairs. One there, and once again, we have the same guy in the middle, which is one there. So we'll start here at the bottom again. 1, 2, and 3. And this carbon would also be sp2 hybridized. Any questions on that there? All right, so let's see if we can account now for all of our bonds that we got going on in this particular molecule. And what I'm going to do is, what I'm going to do, I think what I'm going to do is borrow this space over here, I think. So I'm going to get rid of this here. Now we got that going on. And I'm going to just redraw it here so we can kind of just label all the bonds and everything. And so we got a C, we got a double bond, we got a C. I'll just go this way just to save some room. It doesn't really matter. All right, so I'm just going to call this bond number 1, bond number 2, bond number 3, bond number 4, bond number 5, and bond number 6. So we basically have 6 bonds happening in this particular compound. We want to see if our hybridization can basically account for everything that we got going on here. So just to show that it does, we basically have 2 carbons. And what's going to happen again is we will have our 2s that has a couple of electrons. We have our 2p that's got a couple of electrons. We're going to send this electron upwards here, and that's going to give us an electron in each of those. And obviously we still have our 1 electron over here. In this particular case, though, right, when it goes through hybridization, it is only going to hybridize as sp2, which means we're going to get this situation occurring. 1s and 2p's are going to hybridize. Because I am hybridizing 3 atomic orbitals, how many hybrid orbitals should I end up with? What do you think? Take a guess. I got all day. Yeah, so if I hybridize 3 atomic orbitals here, how many hybrid orbitals should I get? I should get 3. So for every atomic orbital that goes through hybridization, you get a hybrid orbital out of it. So this should hybridize as 3 equivalent sp2 hybrid orbitals. Each of them, as you can see there in the box, has 1 electron in it. It also has 1 unhybridized orbital here, right? So we also have 1 2p, which is actually 2pz, unhybridized. This is just your regular old p orbital, yeah, figure 8 type of deal. So this is carbon number 1. Now, carbon number 2 is the exact same hybridization, which means it's going to end up the same. So we have basically the same deal happening here. If I could draw a straight line, we have sort of the same deal happening there. Let's try that again. There we go. So we're going to go 1, 2, 3. Again, sp2. We'll have an electron in each, and this is our second carbon on the right. And we also will have one unhybridized 2pz orbital happening here, right? All right. Now, in addition, on each of those carbons, we basically have a hydrogen atom, right? And each of those hydrogen atoms will not hybridize. They will essentially be unhybridized, right? 1s orbitals, so just to give us a little room here. I'm just going to draw those in, and again, just drawing them in on the page, not anywhere in particular. So I'll do a 1s hydrogen orbital here. We'll do kind of a 1s hydrogen orbital here that obviously has an electron. And on the other carbon, we got the same deal happening. We got a 1s hydrogen orbital, and we also have another 1s hydrogen orbital. All right, so now we're ready to kind of do all of our bonds, right? So we will start with bond number 1 here. So that is between a carbon and a hydrogen. So it's between this carbon and this guy is going to make our first bond, right? And they each can make a bond. They have one electron each. Sharing of electron, right, gives us a pair of electrons that's shared between the two. That is a bond between an sp2 carbon atom and a 1s orbital. We also have a bond here, number 2, also between a sp2 carbon atom there and a 1s orbital. So that's number 2. I'm just going to take care of all my hydrogens here. So bond number 3, other carbon, same deal. We have a bond between our sp2 carbon atom, hybrid orbital, and our hydrogen. And lastly here, bond number 4, come in between this guy and this guy perhaps, making our bond here. So we've now accounted for, right, all of our outside bonds. By the way, every one of those bonds we just made, those are all sigma bonds. So this is a sigma bond, this is a sigma bond, this is a sigma bond, and this is a sigma bond, basically. All right, so what do we have left? We have left our double bond, right, that we have to kind of deal with. So a double bond is oddly 2 lines, yeah. So the first line, as you might be able to see, is what do we still have left between our 2 carbons in terms of orbitals? We still have a hybrid orbital on the carbon on the left and a hybrid orbital on the carbon on the right. That's going to make bond number 5 there. You want to think about it, the first line in your double bond action there. So bond number 5 is actually going to be a bond between these 2 guys. And that's going to be bond number 5. Basically, in this case, between 2 sp2 hybrid orbitals are going to come. This is also going to be a sigma bond as well, yeah? So basically, every first line that you draw, if it's a single bond, if it's a double bond, or a triple bond, that first line is a sigma bond, basically. Now, what is left is number 6, the second bond to our double bond here, right? We are all out of, as you can see, hybrid orbitals, right? There is no other place we could make a bond at this point. But what is still left that we could perhaps make a bond from? What's still left? It's our unhybridized p orbitals that each have an electron in it. And these unhybridized p orbitals can actually make the second bond there, if you will, for your double bond. It is actually a different type of bond that occurs. And this is where, you know, I apologize for bad artwork here, but I failed it 3 times, but I'll try my best here. So I can actually get rid of this molecule since we have the other one there. So our unhybridized p orbitals are basically just regular old p orbitals. So carbon number 1's got one of those. Carbon number 2 has got one of those. And these unhybridized orbitals are actually going to overlap, and they're going to overlap differently than what happens with a sigma bond. So a sigma bond, they just head straight at each other, and DU is referred to as head-to-head overlap. What happens with unhybridized p orbitals is they overlap what is referred to as above and below the plane of the molecule. And this is what is known as sideways overlap. So they overlap sideways above and below. And this type of bond is what is known as a pi bond. Yeah, so this is a pi bond. I'll leave the E off, even though it does sound good right about that, but we'll leave the E off. So it is a pi bond. And that is what's going to happen right here. These two guys are going to overlap sideways using those p orbitals, and it's going to make a pi bond, which will account for basically the second line that we see in our double bond. So here through hybridization, we're able to account for all those bonds that we see in this molecule, including the double bonds that we see there, along with all the single bonds. Any questions on any of that there? So a single bond, basically going to be a sigma bond. A double bond, which is made up of two lines. First line is going to be a sigma bond. Second one is going to be a pi bond. So that's what makes up basically a double bond. Any questions on that there? All right, so clearly that's double bond action. So you know there's got to be some triple bonds. So let's take a look at what's going on when we actually triple bond something here. So if we take a look at C2H2, if you draw the Lewis structure for this, again, we got two carbon atoms, 1 and 2, and we got this going on here. All right, so you take a moment for each of those carbons, decide what is the hybridization you got going on there. All right, so let's take a look again. You just want a simple way to figure out hybridization. I go with the visual approach. You probably won't mess it up, I imagine. So again, the important part here is just to count up our electron pairs like we're doing geometry. So pretty much everybody counts as one. I'm again going to just draw this. I'm going to put my hand over this side of the molecule first, and that's going to take me to our first carbon on the left, which has one electron pair. And again, even though it's a triple bond, it's going to count as only one. So that's two. So that's a 1 and a 2. That means that is 1s and 1p. So this should hybridize as sp in this case. Any questions on that there? Same thing, we're now going to kind of move our hand to the other side, our blue marking there, and we're going to pop on there a little hand over this side here. And we're going to do the same thing. We're going to count everything up there on our second carbon, and it's going to come out in this case the same. We have one electron pair there, and again that triple bond is going to count as only one. So starting at the bottom here, 1 and 1, that again is going to tell us that this guy is going to be sp hybridized as well. That is again that linear geometry, 180-degree difference between them. Any questions on that there? All right, now in this case, when we look at our carbon, which has basically our 2s electrons that are valence electrons and are, in this case, 2p that are valence, we are going to get, again, that promotion up to our empty p orbital, which is going to put an electron in each of these guys. Difference, though, is the hybridization in this case. We're actually only doing sp hybridization, which means we're just going to take these guys, right, to hybridize. Now, since I took 2 atomic orbitals, I should end up with how many hybrid orbitals? 2, thank you. Just want to make sure I'm not here alone. All right, so that's 2 hybrid orbitals. They're going to be sp. They both have an electron in it. And now in this case, though, we are going to have 2 unhybridized p orbitals there. So we will also have those guys that have, that's like the 2py, 2pz orbitals that are unhybridized, right? And that would be carbon number 1. And much like the other one, in this case, carbon number 2 happens to be the same. It's not always going to be that way, but in this case, it happens to be the same. So it will hybridize the exact same way. It will come up with 2 sp hybrid orbitals and 2 unhybridized p orbitals here. and that's going to be carbon number 2. So again, if we kind of go through our bonds and everything like we did previously, maybe I could save that. That work. So if I were to just sort of number each of these bonds now, and we'll go through and see how we make all those bonds. We'll call that number 1. We'll call that number 2. We'll go number 3 there, number 4, the middle guy, and number 5 up there, up on top of our triple bond. So once again, in this situation, on each of those carbons, we have a hydrogen that's hanging out, and that's going to be a 1s orbital hydrogen. And I'm just going to kind of just draw it in so we can see it as well. So we'll have a 1s hydrogen here on each side. So now we're ready to make our bond. So we can start again on the outside, kind of work our way in. We will go with our first one here, which is between our carbon number 1 and our hydrogen. That's going to make here a sigma bond, right? So it's just one line. We also have number 2 over here, also between the carbon and the hydrogen. So we'll just go this way. That's going to make number 2 bond happening there. At this point, we have left our triple bond. So just like we saw before, by the way, that is also a sigma bond happening there. Our first sort of line, if you will, our bond for our triple bond number 3 can occur between the 2 hybrid orbitals here in carbon, since they are left over. And that's going to make our third one, which is also a sigma bond, right? So we have basically 2 bonds to go to make our triple bond full again. We saw in the last one that we're going to use, obviously, and as you can see here, the only things left are our unhybridized p orbitals. So we're going to use them. We have 2 sets of unhybridized p orbitals, right? We have one really on the y-axis and one on the z-axis. And again, this is where the drawing is going to really be bad. So I will again apologize up front. So we'll have a set of p orbitals that are unhybridized on each of the carbons, carbon 1 and carbon 2. And I'm going to draw it a different color. And on sort of a different axis here, we have another set of p orbitals, you know, the y or the z. And what we're going to get here is sideways overlaps for each of them. So for example, these 2 guys will come together to make bond number 4 there, perhaps. And those guys are going to do, again, sideways overlaps. And lastly, we have bond number 5, which is our last line here in our triple bond, which will be these 2 guys, number 5. And those blue guys are also going to do a little bit of overlapping happening. We saw previously that when p orbitals overlap sideways, which is what's happening here, those are not sigma bonds, but those are referred to as pi bonds. So both of those would be pi bonds. So what makes up a triple bond, if you just want to kind of go through the lines, first line is a sigma bond, and you end up with 2 pi bonds, because in a triple bond situation, you're going to have an sp hybridized orbital. That's going to leave 2 unhybridized p orbitals available to make your double bond, then your triple bond availability there to do so. Any questions on that? Once again, here we can see that hybridization accounts for everybody there, all the bonds that we see down to the Weiler there. Any questions on that there? So let's say we had something like this. Let's say we had, let's do this. Let's do this. Let's do this. Let's do. feel like I just had fun drawing things. I'm almost out of paper, so that's good. All right, so the big question of the day here is, I don't know, for carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6, oxygen 7, oxygen 8, why not? What is the hybridization of each of those? How many total sigma bonds are there in this entire thing? And how many total pi bonds there are? Give it a go, see what you come up with. I'll do it as well because I clearly was just drawing crap on the page there. All right, so see what you come up with. So we're looking for individual hybridization for everybody that has a number, even the oxygens on the outside, why not? And also total in the entire thing, how many sigma bonds should there be and how many pi bonds should there be? Okay, let's take a look and see. So we're gonna start with the hybridization first. So again, if you want to use kind of the checkoff move here, pretty good one. Maybe D. All right, we'll start with carbon number 1 here, which is counting electron pairs like we're doing geometry. 1, 2, 3, and 4. 1, 2, 3, and 4. That's an S and 3 Ps. So that's an sp3 hybrid orbital. Any questions on that one there? Coming to carbon number 2, we got a 1 electron pair, 2 electron pairs. Remember, our double bond only counts as 1, so that is 3. So starting down here, 1, 2, and 3, I'll just circle the bar of the same one. We have used 1s and 2 p's in that case, right? We did not need, obviously, this one here. And that would then mean that this guy is sp2 hybrid orbital there. Any questions on that one there? We'll go number 3, which is 1 electron pair, 2 electron pairs, and again, double bond only counts as 1, so that's 3. So again, starting down here, 1, 2, and 3, that would also be an sp2 hybrid orbital. Going to number 4 there, 1 electron pair, 2 electron pairs, and again, this guy's only going to count as 1. Going to hit us the same here, 1, 2, and 3, and that is 1s and 2p, so sp2. We'll go to carbon number 5 up on top. That is 1 electron pair, and again, our triple bond's only going to count as 1, so that is a grand total of 2 for this guy here. So we'll just get rid of some of that there. So again, starting at the bottom here, 1 and 2, which means that's an S and a P. So that is sp hybridized. Going to carbon number 6, that is 1 electron pair, 2 electron pairs. Going to hit us the same one here, an S and a P, sp. Any questions so far in any of those carbons? That is as quick as you can do it, I think. Yes, in terms of the hybridization. Now, number 7, we can apply it to other atoms, even outside atoms. We're going to do it the same way. So we have here for our oxygen, 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs. So that is 1, 2, 3, 4. So that's an S and 3 Ps, which means my oxygen here is sp3 hybridized. And lastly, my oxygen up there that is double bonded. If we were to apply hybridization to this, we again would do the same deal. Double bond only can count as 1, 2, and 3 electron pairs. 1, 2, 3, a little sp2 hybridization there. Any questions on how I got any of those hybridizations? All right, so now we're going to do the total number of sigma bonds and pi bonds. So I'm going to highlight because I'm probably going to miscount along the way. Basically, sigma bonds are like our single bonds, first lines, and double bonds or triple bonds. So that's, I go green on sigma. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now I skipped all the double bonds and triple bonds, so I can come back to them. 11, right? One line from our double. 12, one line for that double, and 13. So I don't think I missed any. I hope, yeah. So that is all of our sigma bonds in here. Was it 13 I counted there, I think? 13. Now, pi bonds are basically, if it's the double bond, it is the second line. And if it's the triple bond, it's the second and third line, and it's a pi bond. So we'll go whatever color that is there, purplish. So we have a pi bond hanging out there. We have another one hanging out in our double bond there. And our triple bond, it kind of went over on the bottom one there. We got one there and one there. So we do have, it looks like 4 in this case, if I am not mistaken, along the way. Any questions on any of that there?